The Good day, everyone. My name is Vikas Kumar, Assistant Professor, Department of Computer Science, IIMT College of Science and Technology, Greater Noida. Today, I am delivering a lecture on quantifiers. Quantifiers are used in linguistics as well as in logics. So, my topic is about the quantifiers in logic, which plays important role in mathematical logic and computer science. The contents for this lecture are quantifiers, definition and type, examples, use of quantifiers, and conclusion of this lecture. Basics. Here we will talk about a open formula. Open formula is Px, x holds some property. When our subject x follows some property, then we say Px. It is an open formula. Universe of discourse. Universe of discourse is denoted by D, and it is a set of objects when our object x assuming values from which. Quantifiers, this is the definition of quantifiers. In logic, a quantifier is an operator which specifies how many individuals in a domain of discourse satisfy a open formula. As I already told, quantifiers, domain of discourse, and open formula. These three are the main part of this lecture. So, quantifier tells us how many objects of a set satisfy open formula. The quantifiers are of two types: universal quantifier and existential quantifier. Universal quantifiers is used when all elements satisfy the open statement or a formula. And the existential quantifier is used when not all elements satisfy, but some elements satisfy the open formula. It is a case of existential quantifier. We can see here if this big oval marked as D represent set of discourse and a small circle A is some set of objects which is completely lying in this big set D. If all element of this big set D satisfying a formula, it is a case of universal quantification. And if some elements which belongs to A of D satisfying a formula, then it is a case of existential quantifier. Universal quantifier is represented by the symbol turned A or upside down A, and it is used to encapsulate the phrase for all, meaning for all x px is true if and only if px is true for all elements of set of discourse. Here I have mentioned we are taking any value from set of objects or universe of discourse. It will be the property Px will be satisfied for every element. Here I have one example. This example is explained on next slide. See, we are saying for all x square is greater than or equal to 0. That means the square of a number is known negative. Numbers can be considered as natural number or integers or real numbers. I am taking an example of integers here. Let Z be a set of integers, then this set will comprising negative numbers, positive numbers, and a number 0. So I am explaining by first taking positive numbers. The square of positive numbers is always positive, we know. So we can see the square of every positive numbers is known negative. If I am taking in this second case, I am taking negative numbers marked in light blue ink. So x square is again positive because the square of a number is positive. And moreover, if I am taking 0, then the square of 0 is 0 itself. So the conclusion by these three inequalities, the every number which is from set of integers is known negative. So we notice that this x square greater than 0 is a property. So here this x square is greater than 0 is Px, and the set of integers is universe of discourse. In this whole lecture, we will talk about the set of discourse property and how many objects are satisfying that property. So we notice that the all objects x from set of integers satisfying this property. So it is a case of universal quantification. These are the remarks. Let we have some set D comprising k values which are n1, n2, n3 and nk. If we are saying for all px, that means for all x, px is true. That means sometimes px is n1, sometimes it is n2, and x will be n3 and nk. If we are saying the all values from D satisfying this property, that means the property is satisfied for n1 and property is satisfied for n2 and so on up to property is satisfied for nk. That means property is individually true for first element n1, second element n2, third element n3, and last element nk. So this property px is true for each and every element of D. So it is a case of universal quantification. Remark number 2, a sentence for x, px is true if and only x, px is true for every element. This is we have talked in last slide. The remark 3, a value for x for which the predicate px is false, that means it is a counter example of universal statement. Okay. Sometimes there exists some value for which property is not true. It is a counter example. And if the statement for all x px is false, if and only if px is false for at least one x in D. That means to say, if we are using universal quantifiers, then the property must be true for each and every element. And in reverse manner, the if universal quantifiers is not true, that is false, if any one of object do not follow that property, then it will be case of remark number 4. The second quantifier is the existential quantifiers. Sometime, as we have already talked, not all elements satisfy a property or open statement. Only some elements or some objects of that set of discourse satisfy the property. Then it is a case of existential quantifier. Existential quantifier is denoted by symbol this reverse E, which means there exists. Here there is an example. Px is a property, the positive integers which are less than 3. Px is a property, the positive integers which are less than 3. And here we are taking the universe of discourse is Z. That means X is assuming values from this Z. Then we notice that the positive integers which are less than 3 are 0, 1 and 2. Because Z is a set of all the integers. Some integers are negative, some integers are positive. So only 0, 1 and 2 are the positive integers which are less than 3. So every element of set Z is not satisfying the property Px, but the some elements that are 0, 1 and 2 are satisfying this property. So it is a case of existential quantifiers. The meaning of existential quantifier, suppose Px is predicate or an open statement or open formula, and D is used to indicate the domain of X. That means universe of discourse. The statement will be form of there exists X belong to D such that Px is true. This is denoted by, I have mentioned in note 1, if I write there exists xpx, that means the px is true for some elements x of universe of discourse D. The note number 2, the statement there exists x px will be false if and only if px is false for all elements in D. Remark number 2 or note number 2 means If this statement there exists x px is false, then we have to prove this px is false for each and every element of universe of discourse. That means remark number 2 says existential quantifiers is a opposite case of universal quantifier. Example, here is example of existential quantifier. Let px be a open statement. That open statement is x square minus 4 is 0. If the px, a open statement which is saying x square minus 4 is 0, satisfy this equation, there exists x for r px. That means we are saying there exists a real number, there exists a real number which satisfying the formula px, that is x square minus 4 is 0. Means x square minus 4 is 0, then we will get some values of x such that x belong to set of real numbers. We are solving this quadratic equation, and we are getting the values for x are plus 2 and minus 2, two roots or two solutions of equation x square minus 4 is 0. So we note that this number 2 belongs to set of real number, as well as this number minus 2 also belong to set of real number. So we can say there are two real numbers which are 2 and minus 2, which following the formula x square minus 2. So not the all elements of R satisfying this formula, but only two or only few or one or two elements are exist which satisfying this formula and belong to set of real number. So we are using the symbol there exists x belong to R, px is true. So this example serve as an example of existential quantifiers. Remark, if I have already given an example like this in universal quantifier, now I am giving the same example for existential quantifier, and we will try to find what is difference between that example and this example. Okay, let n1, n2, n3, nk are a set, and this is universe of discourse, and we are trying to explain existential quantifier case. Then if we are saying there exists x px is true, so that means either this property is true for first object n1, or this property is true for second object n2. Sorry, this is by mistake, this is written p n1, it should be p n2. Okay, now and either this p property is true for n3 third object. That means for these k objects, if property is true for any one of these objects, then we will see there exists x px, and we are using symbol this capital V is logically known as or logical disjunction. I have explained in detail Pn1 is true or Pn2 is true or Pn3 is true, but not true for each and every element of set of discourse. The conclusion, in conclusion, the quantifiers are useful tool in mathematical logic. These are two: universal quantifier and existential quantifier. When all elements of set of discourse satisfy a property, then it is a case of universal quantification. And when not all, but some elements of set of discourse satisfy a property, then it is a case of existential quantifiers. That's all for this lecture. Thank you all for kind attention. Thank you very much.